Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. Welcome to my AP Physics exam preparation video series. Over the next few weeks, I will prepare a sample video for each of the 4 AP Physics exams to be released each week to help students see what kinds of free response questions will be asked and how the AP Physics exam will ask them to demonstrate their knowledge. As a tutor working with students all over the country, I know that not every student has the opportunity to work with released exam materials prior to exam day. Some instructors choose not to use these materials, and in some cases, especially at some independent and private schools, the school does not call the course AP Physics so that they have more freedom in what they can teach, but the students take the exam anyway. And this video series is primarily intended for those students who have not had access to the released materials in their preparation. AP Central lists the following types and number of free response questions students can expect to see on the AP Physics C Electricity and Magnetism exam. There will be one on experimental design or that has a lab-based component. The questions on the whole will assess all 7 of the science practices: visual representations, question and method, representing data and phenomena, data analysis, theoretical relationships, mathematical routines, and argumentation. Today we'll be taking a look at the E&M exam question from 2015, number 3. We're looking at questions that handle multiple topics this week, and this one handles Faraday's law, Lenz's law, and Ohm's law. A circular wire loop with radius 0.10 meters and resistance 50 ohms is held in place horizontally in a magnetic field B directed upward at an angle of 60 degrees with the vertical, as shown in the figure below. The magnetic field in the direction shown is given as a function of time by B of t equals A times the quantity 1 minus BT, where A equals 4.0 Teslas and B equals 0.20 per second. And you can see here an edge-on view of the loop and a perspective view of the loop. Part A, derive an expression for the magnetic flux through the loop as a function of time t. So we're first of all going to remember that our magnetic flux can be found as the integral of the magnetic field, dot dA. Didn't quite get that written very neatly. And this one is just a simple product of the magnetic field and area. There's no more complicated integration. So we can write this as BA cos theta, where theta is the angle between the magnetic field and the normal to the loop. And our area, because it's a circular loop, is going to be pi r squared. And now we are ready to substitute, again, didn't get that written quite as neatly as I'd like. Now we are ready to substitute that function for our magnetic field, 4.0 times 1 minus 0.2 times t, times pi times our radius squared, that's 0.10 squared, times the cosine of that 60-degree angle, and we are left with, once again, writing is not my strong suit tonight. So I got a magnetic flux equal to 0.063 minus 0.013 T. So scoring, we're going to have 1 point for properly using a correct equation to calculate magnetic flux. Our second point is for correct substitution of area and trig function. And then our third point is for correct substitution into the above equation. Part B, calculate the numerical value for the induced EMF in the loop. And let me grab a fun color. All right, so we're going to remember that the induced EMF is equal to the opposite of the derivative with respect to time of the magnetic flux. It's Faraday's law, right? So our EMF is equal to negative d phi dt. So EMF equals negative d dt of that expression that we just had for our flux, 0.063 minus 0.013t. And that gives us a value of the EMF. I'm going to make that look a little bit neater. Hold, please. So that gives the value of the EMF of 0.013 volts. And our points here, a point for a correct equation to solve for the EMF. There we go. I lost my stylus visually. It happens sometimes. And then our final point is for an answer consistent with part A. So if you didn't find the flux correctly in part A, but you used it correctly in part B, you would not be penalized a second time. And it was also important to note for this one, oops, that's not where I wanted to write. I just needed to find that silly cursor. And actually, we'll put this one in red. So we have a note that any sign on the answer was ignored for this one. Part C, part 1, calculate the numerical value of the induced current in the loop. All right, so what do we know? We know a resistance, and we know an EMF, induced EMF, so that suggests Ohm's law. Oops, and I didn't mean to write that, but of course I just sometimes can't quite find my cursor. So our EMF is going to be equal to current times resistance. So our current will be equal to that EMF divided by the resistance. So 0.013 divided by that half ohm resistance. And I got a value of 2.6 times 10 to the negative fourth amperes. And our point here for C1 was for substitution into Ohm's law. Consistent with the answer from part B. So again, if you didn't find the correct EMF in part B, but you used it correctly in part C, you could still get full credit for this part. And now, what is the direction of the induced current as viewed from point P? Clockwise or counterclockwise, justify your answer. My pro tip on questions like this is do the justification first and then come back and enter your answer second, because you can't select clockwise or counterclockwise until you've reasoned this through. So write out your thinking and then make your selection. So for this one, when we look down at the loop from P, the vertical component of the magnetic field of the loop is upward and decreasing. To oppose this change, the current in the loop must create a magnetic field that is directed upward at point P. Let's just say at point P, sorry. And this requires a counterclockwise current in the loop. So our points awarded here are for a justification that incorporates that the original magnetic field is changing. So and the second point, I'll just try and fit it all in down here, is for a justification that correctly relates the induced current to the direction of a new magnetic field created by that current. So here we are using Lenz's law. Part D, assuming the loop stays in its current position, calculate the energy dissipated in the loop in 4 seconds. All right, so I'm seeing energy dissipated, and I'm seeing a time interval. So this is suggesting to me some kind of power relationship. So in this case, energy equals power times time. And we can recall that power in something involving circuit elements can be calculated as I squared R times T. Well, power is I squared R. Here, because it's energy, we're going to multiply by time. Or you could also, let me actually rewrite that just a little bit better. You could also substitute here the EMF divided by R for power multiplied by time. So when we do our substitutions, we're going to have our 2.6 times 10 to the minus 4th times 50 ohms times 4.0 seconds. Or we will have our 0.013 volts squared divided by 50 ohms times that 4.0 seconds. And in either case, we are going to get 1.4 times 10 to the -5th joules. And now for scoring, we are going to have 1 point for a correct equation to calculate the dissipated energy. And our second point is going to come from substituting into this equation the answer from C part 1 or from part B, depending on which way you did the calculation. Part E, indicate whether the net magnetic force and net magnetic torque on the loop are 0 or non-zero while the loop is in the magnetic field, and justify both of your answers. You know my approach, justify first, then make your selection. So, since the current changes direction relative to the magnetic field as you go around the loop, the magnetic field will exert force of equal magnitude but opposite direction on opposite sides of the loop. These forces all cancel out, resulting in 0 net force. However, since this force is up on one side of the loop and down on the other, this will create torques that rotate the loop in the same direction. Therefore, the net torque is not 0. And for our scoring, all right, there we go. We are going to have a point for selecting both 0 for net force and non-zero for net torque. Sorry. Oh, there we go. Yeah, I couldn't find my cursor. These light colors are very difficult to see. So you get 1 point for selecting both. Okay. And then you get 1 point for indicating that the forces on opposite sides of the loop are in opposite directions. So let me underline that piece. So there is a point. Get a point for concluding that the forces cancel and the net force is 0. All right, so there's our next point. And then a point for indicating the torques add and the net torque is not 0. So this final couple of phrases, this will create torques that rotate the loop in the same direction. Therefore, the net torque is not 0. That would earn us our final point on this part. And a note that the final point on this question was awarded for correct units on at least 2 parts with a calculated numerical answer and no incorrect units. So I hope you have found today's demonstration of a very typical AP Physics C electricity and magnetism exam question that covers multiple topics helpful. If you have a video solution request for YouTube, you can send it to physicsproblemrequests@gmail.com, though I'm not going to be working on those until after the AP series is over. If you would like some email assistance, you can reach me at freephysicshelpline@gmail.com with a limit of 10 questions per academic year. If you'd like to learn more about my online physics tutoring services, you can email me at brandyheflinphysics@gmail.com. You can visit my website, virtualphysicsofficehours.com, and you can find me on Facebook. I'm Physics Tutor Brandy. Just a few notes. AP is a registered trademark of the College Board. The College Board does not endorse or recognize this video or my services. All of the materials presented are available on AP Central at the link shown here for the AP Physics C Electricity and Magnetism exam. And those materials include the released free response questions, the scoring guidelines, and sample student responses and commentary. I strongly encourage students to review those sample responses to get a feel for the different levels and quality of the responses prepared by the students who took these released exams live, and to see what the scorers for that year were looking for and how they decided to award points. If you have any questions, you can reach me at brandyheflinphysics@gmail.com. I'm Physics Tutor Brandy. I love physics, and I love helping you. Until next time.